Warning: do not copy. Our programs are covered by registered U.S. copyrights. They may not be duplicated or copied. Willful infringement constitutes a felony punishable by fine and imprisonment. Civil remedies include statutory damages of up to $50,000 per offense, plus plaintiff's attorney's fees.
Multimeters explained. Voltage and current. Now that you've learned how to perform continuity tests and measure resistance, let's take a look at how to wire simple circuits by reading schematic drawings, and how to perform voltage and current measurements using analog and digital multimeters.
Now, let's look at the components needed to build your circuit. You will need a breadboard, a 6-volt battery, 2 resistors, one rated at 2.2 K and the other at 10 K, and 2 lengths of thin, solid wire connected to alligator clips. The breadboard is used to build temporary circuits. It acts as a base supporting the components and providing electrical connection between them. The electrical connections are made by tiny metal bands beneath the holes on the back of the breadboard. This breadboard is divided into a top and bottom half. Each vertical column of holes is connected together in this main group on the top half, as is each vertical column in this group on the bottom. A wire placed in this hole on the breadboard will make electrical contact with a wire placed in any of these holes, but it will not make an electrical connection if placed to either side of that column.
This is the schematic for the first circuit. Notice that all of the components are represented by symbols. Here is the schematic symbol for the battery. The longer line on the left side of the symbol represents the positive terminal, and the short line on the right side represents the negative terminal. The resistor is represented by this symbol and is labeled R1 2.2K. The lines between the components represent the wire or the metal bands in the breadboard that connect the components together. In this circuit, the battery and the resistor are wired in series, providing a single path of current flow through the circuit.
To construct the circuit, bend the leads on the resistor to a 90-degree angle and cut off the excess. Insert the resistor leads into the breadboard, positioning the resistor horizontally on the bottom or top half of the breadboard. Next, clip a wire to the battery's negative terminal and connect the other end to the same vertical column as the resistor's right lead. Connect the other wire to a hole in the same vertical column as the resistor's left lead and clip a wire to the battery's positive terminal. You have now constructed the circuit shown on the schematic. Notice the similarity between the drawing and the actual circuit. When the circuit is not being used, disconnect the battery by removing the alligator clip from the positive terminal.
Now, let's set up the analog multimeter for DC voltage measurements. First, turn the function switch to the positive DC setting and set the range switch to the 50-volt range. This range is chosen for safety because it is well beyond the output of the 6-volt battery used to power the circuit. Then plug the test leads into the recessed jacks labeled common and positive. Use the hook tips or alligator clips whenever measuring voltage and current. This will keep your hands away from the circuit and will provide an accurate reading by maintaining constant pressure on the wire or component leads.
In order to measure the voltage in this series circuit, the multimeter must be connected in parallel with the resistor. Since the resistor is the only source of significant resistance in the circuit, the reading you'll get is for both the voltage drop across the resistor and the total voltage in the circuit. To begin, connect the red or positive test lead to the left side of the resistor and the black or negative test lead to the right side. Then reconnect the power to the circuit. Looking at the meter face, the scale for DC voltage measurements is just below the scale for resistance. This scale reads from left to right and is used for all of the DC voltage ranges. Since you've set the range switch to the 50-volt range, find the 50-volt scale located between the 10 and 250-volt scales. The 50-volt scale starts at 0 and is divided into 10-volt increments. Looking closely, the reading is well below 10 volts. For a more accurate reading, you can now safely set the range switch to the 10-volt range. Now, the DC volt scale measures from 0 to 10 volts in 1-volt increments. The needle is approximately one small line above the 6. Since each volt on this scale is divided into 5 units, each small line represents 0.2 volts. Therefore, both the voltage drop across the resistor and the total voltage in the circuit equals 6.2 volts. When measuring series circuits, the voltage drop, or the sum of voltage drops, will always equal the total voltage.
The next circuit to construct has two resistors. R1, the 2.2K resistor, wired in series with R2, rated at 10K. The first step is to disconnect power from the circuit by removing the wire on the positive battery terminal. Then add R2 to the circuit, so that one lead of the resistor is in the same vertical column as the first resistor. Then insert the wire from the negative battery terminal into the same vertical column as the right lead of the second resistor. To measure the total voltage in the circuit, the multimeter must be connected in parallel with both resistors. Connect the positive test lead on the left side of the circuit and the negative test lead on the right. Then connect the power. The multimeter reads 6.2 volts, which is the same reading you had with one resistor in the circuit. If you check the voltage drop across R1, you'll find that it has changed. It now reads 1 volt. When you connect the multimeter to read the voltage drop across R2, you'll see that it reads 5.2 volts. Remember, the sum of the voltage drops in a series circuit equals the total voltage. Therefore, 1 volt plus 5.2 volts equals a total of 6.2 volts.
The next circuit to construct is a parallel circuit. Notice that the left leads of resistors R1 and R2 are connected together, as are the right leads, allowing a different current path through each branch of the circuit. To build the circuit, disconnect the power from the battery and move R2 so that it is positioned below and parallel to R1. Then insert the negative battery wire in the same column with the right leads of both resistors. This time, let's use the digital multimeter to measure the voltage. First, turn the rotary switch to select the volts DC function. Then, plug the test leads into the recessed jacks labeled with the letter V and COM and connect the hook tips. To measure the voltages in this circuit, connect the multimeter in parallel with R1, then connect the power to the circuit. The reading is 6.32 volts. Next, connect the multimeter in parallel with R2. The reading is the same for R1, 6.32 volts. Therefore, in a parallel circuit, the voltage drop across each resistor is the same, even if the resistance values are different.
Now, let's see how to measure current, starting with this series circuit. Notice that the multimeter is connected in series with R1 for current measurements. To begin, disconnect the wire to the positive battery terminal and remove R2. Turn the digital multimeter off and move the positive test lead from the jack labeled with the letter V to the jack labeled 300 milliamps. Then select the amp's DC setting on the multimeter. Connect the positive test lead to the right side of the resistor. Then lift out the negative battery wire and connect it to the negative test lead. The multimeter is now in series with R1. Connect power to the circuit. The multimeter indicates that the total current in this circuit is 2.88 milliamps.
Next is the series circuit incorporating R1 and R2. Again, the multimeter must be connected in series for current measurements. First, disconnect the power to the circuit and insert R2 in series with R1. Then, connect the positive test lead to the right side of R2 and the negative test lead to the negative battery wire. Now, power up the circuit and check your reading. The multimeter measures a total of 0.53 milliamps. In this series circuit, you will get the same reading for total current at any point in the circuit. Let's connect the multimeter to the left of R1 to see if the current measurement is the same. First, disconnect the power to the circuit and attach the positive test lead to the positive battery wire and the negative test lead to the left side of R1. Then insert the negative battery wire into the same column with the right side of R2. Once the power is connected, you'll see that the same reading, 0.53 milliamps, can be found at any point in this series circuit.
Now, let's connect R1 and R2 in parallel and measure the current in each branch of the parallel circuit. Notice that the multimeter is connected in series with R1. To begin, disconnect the power from the battery and insert R2 below R1. Next, connect the negative battery wire to the right side of R1 and R2 and the positive battery wire to the left side. To measure current through the top branch, the multimeter can be connected between this end of R1 and the negative battery wire. You can use a jumper wire to provide a convenient test point.
Let's use the analog multimeter for these measurements. First, turn the range switch to the 500 milliamp setting. Unlike the digital multimeter, the test leads remain connected to the same jacks used for voltage measurements when measuring current levels less than 10 amps. Connect the positive lead to R1 and the negative test lead to the jumper. Then, connect the power to the circuit. Move the range switch to the milliamp setting that allows the largest deflection of the needle without exceeding the scales. In this case, the 10 milliamp setting is best. When measuring current on an analog multimeter, use the same scale that you used for voltage measurements. With the range switch set to 10 milliamps, the scale measures from 0 to 10 in 1 milliamp intervals. Each milliamp is divided into 5 smaller intervals, each representing 0.2 milliamps. Since the needle is 4 small lines past 2, the measured value is 2.8 milliamps.
Now, let's check the current flow in the bottom branch. First, disconnect the power. Then, reinsert R1 and pull out the right end of R2. Connect the positive test lead to R2 and the negative test lead to the jumper. Apply power to the circuit and check your reading. The needle barely moves. Try turning the range switch to the 1 milliamp setting. The needle will now provide a more accurate reading.
When set to the 1 milliamp setting, the scale measures from 0 to 1 milliamp, with each of the larger lines on the scale representing 0.1 milliamp. Each smaller line represents 0.02 milliamps. Since your reading is one small line past 0.6, your measured value is 0.62 milliamps. As with voltage in a series circuit, 2.8 milliamps in the top branch plus 0.62 in the bottom branch should add up to a total current value of 3.42 milliamps. Let's see if you get that value when you measure the total current. First, disconnect the power and your test leads. Then reinsert R2 and pull out the negative battery wire. Then connect the positive test lead to the jumper and the negative test lead to the negative battery wire. Set the function switch to the 10 milliamp range and apply power. The multimeter indicates approximately the same total current value as in your equation, 3.4 milliamps. Now, let's review what you've learned in this program. You've learned how to use schematic diagrams to construct series and parallel circuits, and how to measure voltage and current using analog and digital multimeters. This completes the program on voltage and current measurements.